So, hello, welcome to my channel. This is my first video of this sort of thing. You know, you can have me as some like background noise or while you're doing something, to feel like you're someone's talking to you, and there's also so I can feel like I'm talking to people while I'm yapping about things that I like that are incredibly niche, you know. So, so yeah, I tried doing this sort of video uh twice already. I just finished the second attempt. Somehow my camera just stopped working in the middle of the recording. Yeah. I was 25 minutes deep. But anyway, and the last time, the like 2 weeks ago, I went and I tried doing Reddit math questions. Like I went to some subreddits and tried to do some math questions. I got an hour in and I did not record my iPad screen. It's like, hopefully, hopefully this this time is the right time. Okay, hopefully. Ah. So anyway, this time, however, I'm gonna be doing some of the problems from this wonderful book. Just called complex variables. Uh, so yeah, I just got done reading through the first, I think it's the first chapter. Let me see the index. Yeah, first chapter. The first chapter, which introduces the complex numbers. Um, there's like a there's like bigger and bigger subsets. So like it starts with the natural numbers like 1, 2, 3. Then it gets to the integers, so it's like -1, 2, -2, 3, right? Then it gets to rational numbers, which is numbers that can be represented into fractions. And then it gets into irrational numbers, like square root 2, which are decimals that cannot be represented by fractions, which makes up the real numbers, the set of all real numbers, and then we're introduced to the complex number system, right? The imaginary number system, right? And then we're introduced to some basic arithmetic that you can do with the imaginary numbers, uh, like addition, subtraction, multiplication, division. We can choose the absolute value. I'm gonna have to review that probably after this video. There's a lot of of problems in this book. So yeah, the equality, we introduce some other operations that you can do uh, with imaginary numbers if you treat them as vectors. So like with this book, they kind of introduced like some sort of pseudo vector where you can do some operations on, and for some others not. Or maybe I'm just too dumb to see that they can actually be treated as vectors. Um, in a little bit, you'll see why what I mean, right? So we can start with question one, or like set of questions one, yeah. Which is perform each of the indicated operations. So this basically tries to show, like not on purpose, but I'm seeing that it is showing that the set of all complex numbers is a vector space. So yeah, let's start. First question, once again, which is 3 plus 2i plus -7 minus I, right? So this is why I said that one of the reasons I say that you can treat them as pseudo vectors because it is the same as 3, 2 plus -7, -1. You could treat them as polynomials as well. So if you treat them as polynomials and treat the I, the imaginary part, as some like variable, like an x, it's going to be the same. So 2i minus I is I, and 3 minus 7 is -4. And if you go into on the vector side, it's going to be the same. It's going to be -4, 1, which if we convert it back, it is the same, right? I'm sorry if I'm going too fast in these problems. I just did them a couple minutes ago. I I am right now I am done with this, but I was enjoying this right up until it stopped working. Gosh. So second question. -7 minus I plus, so this is trying to show the commutative law of addition. 3 plus 2i, right? And this is going to be the same. Oh, it's like -7 plus 3 is -4, -1 plus 2 is 1. So it shows the commutative law of addition, right? So next question. We're getting into subtraction, right? So 8 minus 6i minus 2i minus 7. This is another place where you can treat imaginary numbers as vectors. If you do this, right? And also in the same sense of polynomials that you must distribute the negative sign. So this becomes fuck. And this becomes hold on. Right? We get that 8 plus 7 is 15, and -6 minus 2 is -8. And it's the same here. Right? Yeah, so yeah, that's right. 15 minus 8i. So now we're gonna get into, I don't know why they included that specific question. Because we already showed that the commutative law of addition is true for imaginary numbers. I mean, for complex numbers. Sorry. Maybe it's extra practice. Maybe it's extra practice. Probably. So now you get 5 plus 3i. We're gonna show the associative law of addition. We get plus. Sorry. The book uses some curly braces when you're like nesting operations. It's just a stylistic choice. I prefer to use another set of parentheses personally, you know. So you get -1 plus 2i plus 7 minus 5 minus 5i. Right. And this, we can use PEMDAS. We can use PEMDAS, right? -1 plus 7 is 6. 2 plus -5 is -3. I, and 5 plus 6 is 11. and the i's cancel. So you could say this is still part of the complex number system, but it's plus 0i, and since it's plus 0i and it's an integer and it's greater than 0, you can say that this is part of the natural numbers. I think this is how you. I think so. I think this is no. That's definitely not how you, not how you draw the symbol. Hold on. I think that's it. Which is part of the integers, right? Which is part of the real numbers. Um, but since the imaginary part is 0, it is not part of the complex number system. Why you can still attach the plus 0i in the imaginary as the imaginary part, but this is not really regarded as an imaginary number. I mean, as a complex number, is because you can uh, depict the complex numbers as vectors. Like I said, you can treat them as pseudo vectors. Um, and your as vectors in a space where your axes are going to be the real part and the imaginary part. So like for here, we can say that 5 plus 3i. So it's going to be 5 over and 3. That's 5 plus 3i. Actually, it is part of. I am fucking stupid. It is part of the complex number system. It is part of the complex number system. Fuck. It is part of the I'm just stupid. Don't listen to me. Just hear me out. Ah, God. This can be regarded as 5 over 3. But if the imaginary part is 0, then it's just a flat line. That's still a vector. Oh my goodness. I don't know what's happening to me. Everything's going wrong today. um. But anyway, next question. Next to the question. Right. So now, since we're showing the associative law of addition, we're gonna move the parentheses over to the first two terms. So it's gonna be 5 plus 3i plus -1 plus 2i plus 7 minus 5i. So here, if we use PEMDAS, it's gonna give us the same. So it's gonna be 6. Right? Yeah, 6 plus 5i plus 7 minus 5i. 6. It's 4. Welcome to my channel. I am very prone to making errors with like things that are heavy on computation like this, but I'm just too lazy to be using my calculator with every single calculation. So welcome to my channel. So yeah, 4 plus 7 is 11, and yeah. All right. So now we're going into, so right now we just showed the associative law of addition with complex numbers. So now we're getting into the multiplication. Not only multiplication, but also the commutative law of multiplication with complex numbers. So, sir, I just took linear algebra, and my linear algebra professor used to say a lot like "sir, sir." It's like his catchphrase. Sir, 2 minus 3i times 4 plus 2i. Right? Yeah. So here, this is one of the reasons I say pseudo vectors. I refer to complex numbers as pseudo vectors instead of full-on vectors, because I do not know how to treat these numbers as vectors when it comes to multiplication. Right? Because in my previous attempt at recording this whole thing, I checked with a dot product as well as the cross product, and none of them worked. So if we try to if we try the dot product, right, this becomes 8. 2 times 4 is 8 plus 6 equals 14. And this is one where for me it was a little bit easier to treat it as treat the complex numbers as polynomials, because I could not find a way to treat them as vectors. Right? So if we treat it as polynomials and we use FOIL, we get 8 plus 2. Yeah, sorry. I just had a brain fart. 8 plus 4i minus 12i plus 6. And we get 8 plus 6 is 14. And we get negative 8. Right. Why did I do plus 6 when we multiply these two? If you know about imaginary numbers, which I suppose you do because you're watching this video. Anyway, if you know about imaginary numbers, you know that they can be regarded as a square root of -1, but in reality they're the set, and I is the set of solutions to I squared equals -1. So if you solve for I, you get the same answer, but this does not paint the whole picture. Right? Because you cannot say it's just a positive part. You have to include the negative part. Right? So if we know that I squared is -1, and we multiply this as taking I and treating it as a variable, we get -6 times I squared, which is -6 times -1, which is +6. Right? Which we get 14 minus 8i. I think that's the right answer. Yeah, 14 minus 8i. So anyway, you get 8 plus 6, 14. We got the real part of a multiplication. If we do cross, we get 4 minus. Hold up, what? 4. What? I just realized, like, it's not say, it doesn't say it in the book that you can do this with multiplication, or it does it. Like, no, it doesn't. It really doesn't. Okay, so I discovered something by myself. I am proud. So the dot product. So for multiplying, if we want to treat them as vectors, to get the multiplication of the complex numbers, you can get the real part of the multiplication by doing the dot product, and getting the imaginary part by doing the the cross product. What? 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 And this is 14 minus 8i. Wow. Yeah, wow. So moving on. So I said that this was the commutative property, so we're gonna do the flip side. The flip. We're gonna flip the terms. So now we're gonna do 4 plus 2i times 2 minus 3i. And we treat them as polynomials. Okay. 4 to the 2 is 8. Minus 12i plus 4i plus 6. 14 minus 8i. And yeah, I want to see if the flip side also works with the cross product. Let me check. So we got 4, 2, 2, negative 3. Hold on. Oh, I did it wrong again. Oh my goodness. Oh my goodness. Never mind. It's negative 3i. It's not 3i. Fucks. For fuck's sake. Negative 3. It does change things. What? Well, let me try. It is negative 12 minus 4, which is negative 16. Right, and this becomes 4 plus 12, which is 16. And this becomes 8 minus 6, which is 2. So now, this is what... I thought I had it. Oh, come on. I thought I had it. And I thought I had it. I thought I found a way. I thought I had found a way to treat the complex numbers as vectors when it comes to multiplying complex numbers. No, you just stick to polynomials. Fucking it. At least you cannot do it with a standard dot product, or as some other people might call, as an Euclidean inner product. Right. Well, actually, you can treat the what's it called, polynomial multiplication as an inner product in itself, right? Right. So let me cook. Let me cook. Time for 24 minutes. Let me cook. So now, what was I gonna say? What was I gonna do? So, say A, B, C, D. So this becomes, well, actually, let's do them as polynomials first so we can see it better. I'm cooking something. Hold on. This becomes AC plus AD. Oh, hold on. D. ADI. ADI. CBI. The CBI minus BD. You could take it as this is described in the book, but it's not explicitly said that you can apply this, so it is like an inner product if you treat them as vectors. Um, so yeah. Hmm. So yeah. So yeah, this is an inner product. Like yes, I know polynomials form a vector space themselves. Yes, I wanted to find a simpler and more simple way of treating them as vectors, but I don't think there's any. Like I think this is the most straightforward way of treating them as vectors. But it's not like some other thing that I'm gonna like try to explain a little further down the video. We are a quarter way through. I am so bad at math. We're a quarter of the way through, kind of. Where were we? Oh yeah, the flip side. We have 4 plus 2i times 2 minus 3i. We do FOIL. We get 8. Wait, did I do this? Okay, I'm gonna skip this one. If I didn't do it, you got the gist of it. Let's move on. So now we're gonna show the associative law of multiplication. 2 minus I times 3 plus 2 plus 2i times 5 minus 4i. We can apply pandas as well as FOIL. I'm sorry, I have a little bit of a cold. We can apply pandas as well as FOIL. So on the inside, we get negative 15. Plus 12i, is it? Negative 3, negative 4. Yep. Plus 12i plus 10i, and then plus 8. Right? This is, yeah, plus 8. I am doubting myself so much. I am so doubting myself now. After that little, like, I thought I had it, but I just missed. I missed the little humble minus sign that is kid. I forgot to add. It's incredible. Amazing. Amazing. Anyway. Um, so this becomes negative 7 plus 22i, 2 minus I, right? And we do FOIL again. We get negative 14 plus 44i. Hold on. Yeah. A little gross. I am sorry. I apologize. 2, so yeah, 44i. We get plus 7i. And then apply the thing. So this is negative 1i times 22i, which becomes negative 22 i squared, which is 22, plus 22. Right? Yeah. So yeah, I am gonna use my calculator here. 22. Don't judge me. 22 minus 4. I know you're doing it. Shut the fuck up. 22 minus 14. This is 8. 8. And you got 44 plus 7. That's gonna be 51. Yeah. I'm just going to do it. To do it myself. 51, fuck, 51i. That's my answer. Yep, that's your answer. A plus 51i. And if we would like slide the parentheses over, so we do 2 minus I times -3 plus 2i times 5 minus 4i forgot what I was gonna do. I just had a brain fart. Anyway, so yeah, this we use FOIL twice, PEMDAS. For this we get -6 plus 4i plus 3i plus 2i plus 2. Sorry, plus 2. This becomes -4 plus 7i, 5 minus 4i, -4 times 5, -4 times 5, -20, -20 plus 16, I plus 40, no, that's 35, 35i, 35i, and this is -16, right? Positive. I just had another brain fart. What is happening? I think I've been doing this for way too long. It's already been an hour. I know it's been 30 minutes for the video, but I just did this for 25 more minutes. This is draining. Gotta say, wow. I don't know how the influencers do it. They just yap about all day, and they do stuff, and wow, I don't know if I could. I guess it's something like that you can get used to, you can get accustomed to. But anyways, I'm gonna do this again. You got -20. You got plus 16i. Right. Then we get plus 35. I. Then we get -28, which becomes a positive 28. And yeah, we got the same. Okay, so 20 plus 28 is 8. And 16 plus 35. Well, I'm gonna do it later. It is 51. Okay. That's 50. 51i. Yay! So now what comes next? I'm gonna move this over because I can't see. Can't see the. Can't quite see the numbers. Yeah. So yeah, it shows another method where it's like you can distribute the this we just saw the associative part where you can into is it intuitive, you can get to the conclusion that you can distribute the outside. You can distribute this for each and then multiply it as so. Not a very efficient way of doing it because the numbers get pretty big. But the numbers can get pretty big if you do it like that. But it is a way. It is a manner. Yeah. Next question. Yay! So here we get into to division. We're getting into division, right? And here it's gonna have like two very drastically different ways of doing it. Whether you treat the complex numbers as polynomials or as vectors, right? So first we're gonna treat them as polynomials for this one. -1 plus I, right? We're gonna treat them as polynomials. So for this, we're gonna take an answer as being able to separate the real part from the imaginary part, right? So we can multiply by the conjugate of the denominator, which would be -1 minus I, right? So it will give us -1 squared plus, well, it was actually minus I squared, yeah, minus I squared would be 3 minus 2I times -1 minus I, right? So we do FOIL, it's -3 minus 3I plus 2I minus 2. So this becomes -5 minus I. And 5 minus I, and we get that I squared equals -1, and -1 times -1 is equal to 1, so this becomes 2. And -1 squared is 1, so 1 plus 1 is 2, right? And here we can already separate. We're about done. So it's -5 over 2 minus I over 2, right? But there is another way of doing it in which you will only have to multiply once and then kind of, I am not really sure. Now that I'm thinking about it, I am not really sure if it's more efficient, but I just found it myself. You can use matrices to divide. Like, you can use matrices to divide complex numbers, right? So we can take this operation as the solution to this other equation. Right, equals 3 minus 2I. Some of you might already see where I'm going, what I'm going to do. We can FOIL once with this, so we can do, sorry, so we can do -A. So we can do -A minus BI plus AI plus AI minus B, right, equals 3 minus 2I. And since we can treat complex numbers as vectors, since the real part and the imaginary part really don't touch, we can separate the imaginary part and the real part here as well. So we get -A minus B equals 3. We get AI minus BI is -2I. Right? And we can put this into a matrix, right? So we get -1, -1, 1, -1. Actually, it's like I, but it's gonna be the same either way. A, B, right, equals 3, -2, I. And if, actually, for this one is pretty simple. So I'm not gonna use my calculator for this. I am about to run out of battery and out of time as well. So let me finish this. So I'm gonna do this by hand this time. But for others, I'm just gonna be using my calculator. I'm gonna be using the Sys. This is a TI-36 Pro, so I'm gonna be using the SysSolve. This solves for systems of equations, right? Pretty self-explanatory. So yeah, we can augment this. -1, -1, I, -I, -3, -2i, right? We can do -r1. We can do -r1. Put it into r1. 1, 1, -3. Right? And we can multiply by I, by -I. So negative r1i is r2, r2. We have 1, 1, -3. It's going to be 0. This is going to be -2i. This is going to become 3i plus -2i is I. Right? And we can divide r2 by -2. And then, well, actually, -2i. We can get rid of the i. It's the same either way. Okay. Okay. We can do -r2 subsequent plus r1. Right? Making it 1, 0, 0, 1. This is -1/2. And 6 over 2, 1/2. This is going to be -5 over 2. It's going to be 5 over 2. Boom. This is the real part. This is the imaginary part. And this becomes -5 over 2 minus I over 2. This is how you do it by hand. But if you have your calculator ready, it's just going to be plugging it in and doing with your calculator. Right? So it's in the end, like if you use calculators, is a more simple way of doing it because you only have to multiply once and then you plug it in, right? But either way, it works. It works. Okay. All right. Wait, let me see how much. All right. So, you know what? I think that's a good place to stop. There's 45 minutes. It's been 2 hours. I spent 2 hours on this. Wow. Wow. Or like an hour and a half, something like that. Wow. Anyway, it's been a good time. This is my first ever video. Hope you liked it. If you want to see more, like, subscribe, whatever you want to do. And I'll see you in the next. Bye.